we've done divergence. Stokes' theorem is the trickiest of those three. Divergence theorem is actually really rather easy. There's only one way divergence theorem can be made hard, or at least slightly tricky, and we'll do that tomorrow. So today we'll kind of do vanilla divergence theorem, and then we'll step it up a little bit tomorrow, and then we're done. The plan was to have finished lectures by next week Thursday. Next week Friday is a public holiday. Because we were already falling behind, and then of course there was yesterday's storm business, chances are high we're going to have to roll over into at least the Monday of that following week, which is technically still term time, but I had hoped to finish early. But we'll see how next week goes, because I did give quite a lot of time to some quite simple topics, so we'll see how it goes. Okay, divergence theorem. A question, yes? No TAT test, because there couldn't be one yesterday. Yeah, so it's not fair to have one for Thursday if not for Wednesday. So there you go. So there's no trigger to leave at 4 o'clock, so you can stay at 4:30. Derek will be waiting. I'll give him your name. Okay, Green's theorem. So first of all, to put it into context, Green's theorem relates... You're just trying to make me not teach. Where? Oh, really? According to this, it's on. Oh, no. According to this, it's on. So what I'll do is I'll power off, and then I'll power back on again. But you know what? I'm still going to write, and you're just going to have to listen with your ears. So what I'm writing while this chills is Green's theorem relates a double integral. Or you can just listen and copy it down later, whatever works for you. But I can't pause. Green's theorem relates a double integral over a region along its boundary, over a region to a line integral, I beg your pardon. Green's theorem relates a double integral over a region to a line integral along its boundary. Okay, you know that. Stokes' theorem, very similar. Stokes' theorem relates not a double integral but a surface integral, relates a surface integral. Okay, all right, it's powered down. Let me just give it a moment. Maybe it needs to do like a cool down or something. Stokes' theorem relates a surface integral over a surface to, just like Green's theorem, a line integral along its boundary. Okay, let me power these back up again and see if they work this time. Okay. So Green's theorem relates a double integral over a region to a line integral along its boundary. Stokes' theorem relates a surface integral over a region, which is a piece of a surface, to a line integral along its boundary. And then what divergence theorem does is it steps all of this up a dimension. So the divergence theorem, any life in these projectors? I'm not, hold on, that one's got a life. And so does that one. Okay, we're getting there. The divergence theorem, which is also called Gauss's theorem, there's a lot of things named for Gauss. Okay, right, and then transfer that to laptop. All right. The divergence theorem, also called Gauss's theorem, relates a triple integral. Yay, it's showing. A triple integral over a 3D region, usually framed as a solid, to a surface integral across its boundary. Because the boundary of a 3D region is not a line but a surface. So if you think about the equations, the expressions that are present in Green's theorem and Stokes' theorem, on the one side you've got two integral signs, and on the other side you've got a single integral sign. In divergence theorem, each of those steps up. On the one side you've got a triple, or you've got three integral signs, and on the other you've got two integral signs. Those two integral signs are related to a surface integral. So a flat region in the xy plane or in any of the coordinate planes, its boundary is a curve. A surface floating in space, its boundary is also a curve. But a 3D solid, its boundary is a surface. But it's still got that pattern of integral of something related to differentiation equaling an integral across the boundary of the region. So there's that sort of rough pattern. If you look at all of these formulas together, you can see a sort of family resemblance between them. Okay, so the actual statement of the divergence theorem, which is probably in a box somewhere, yes, it's in a box on page 69, looks like this. The divergence theorem. Let E be a simple solid region. Now, we haven't actually defined that, but after all the previous definitions, I think you can think it presumably means that it doesn't have any holes in it. Okay, a simple solid region. And let S be the boundary surface of E given with positive orientation. Now, E is some sort of lump, and S is the entire surface of it. And positive orientation for a closed surface, which S surely is outward. So given with positive, which for a closed surface means outward orientation. Let F be a vector field whose component functions have continuous partial derivatives. We always have that, don't we? Have continuous partial derivatives on an open region that contains E. On an open region that contains E, that basically means F has to have continuous partial derivatives within the solid, but also just a little bit outside. It can go a bit crazy somewhere else, but as long as everything is fine and well behaved within the region and just a little bit outside of it, then everything's fine. Then the following formula applies, which I'm giving to you without proof. Here's the surface integral that we have on the one side of the equal sign, and here's the triple integral that we have on the other side of the integral sign. And the reason why it's called the divergence theorem is because the integrand is div f. Okay, now this thing on the left over there is obviously flux. Okay, you'll recognize that. This thing over here is flux. So divergence theorem questions are almost inevitably flux questions. So if you're asked to work out the flux through a surface, you sometimes have recourse to the divergence theorem, and that'll be somewhere in one of these decision trees, the flux decision tree. So basically, if you want to look at it on page 11, what we're basically doing today is the top box on the right there. Okay, is your surface closed? And if the surface is closed, which it is if your surface is the boundary surface of a solid region, then you can use divergence theorem. And then what we'll do tomorrow is the middle box on the right of that decision tree. And what we have done so far in flux questions has been the bottom box in that flux decision tree. Okay, all right, and that's basically it, and then I'll jump into some examples. Let's have a look. That'll be number 52. Find the flux of the vector field, that thing, through the surface of the unit cube. Okay, so we have, oh my goodness, someone's sneezing a lot. Bless you. 1, 1, 1, Z, X, Y. Okay, so we've got that unit cube, and we've been asked to find the flux, and we've been given our velocity field, our whatever you want to call it, our vector field, our force field, if you will. through the surface of the unit cube. Do this, and it says to do it as a flux calculation, but also by using divergence theorem. If you'll forgive me, I will actually not do it straight up flux because we're so short of time at the moment, having fallen behind. But it will go up in the Wöhler solutions, and basically to actually do it by surface integral, the surface integral for flux would actually be 6 surface integrals, because that cube consists out of 6 surfaces. Would be 6 surface integrals. None of them would be particularly hard, because all of them, your n that you would be using in your formula, your unit normal, would either be I or minus I or j or minus j or k or minus k, because each of the planes of the cube is parallel to a coordinate plane. Also, because each of your pieces of surface is parallel to a coordinate plane, your conversion factor in every case would just be 1. So 6 surface integrals, yes, but 6 very easy surface integrals. All quite easy. Okay, and I'm not actually going to do that. It'll go up into the Wöhler solutions. I'd rather jump into divergence theorem. So let's say we got that question. Okay, work out the flux. We'd say, that surface is a completely closed surface. So instead of working out the flux the surface integral way, I'm going to use divergence theorem. I'm going to say, well, we know that our flux, let me call the solid E and the surface S. I don't think we were given names in the question. No, we weren't. We know that this is basically our flux equation. However, divergence theorem says that we can turn this into a triple integral over the 3D region. And instead of doing the surface integral, we can just do the triple integral, which is frequently a lot easier than the surface integral. Triple integrals, even though when all you've ever seen is single variable integration, triple integrals look very intimidating because they have 3 integral signs. But you've done a bunch now, and you know they're not actually particularly intimidating, particularly if your region is very easy to describe, which a cube is. So let's have a look. Div f, that would be the derivative of the first component of f with respect to x, plus the derivative of the second component of f with respect to y, plus the derivative of the third component of f with respect to z, dv. Okay. And then we'll work that out. Ooh, hold on, let me just pause the recording. Yes. Absolutely. So you can find flux in 2 different ways. You can use your straight up surface integral, which is how flux is essentially defined. Or if your surface is a closed surface, you can use divergence theorem. There's a bit of a spin on that, because you can actually use divergence theorem even if your surface is not fully closed, and that's what we'll cover tomorrow. It's the only way you can make divergence theorem tricky. If you look in past exam papers, inevitably if you get a divergence theorem question, it's the kind we're going to do tomorrow. Yeah, pretty much. Not 100% of the time, but most of the time. I said inevitably. Most of the time. Okay, dv. In fact, you know what? I'm not going to do dv. I'm going to jump straight into dx, dy, dz. Dx, dy, dz. X goes from 0 to 1. Y goes from 0 to 1. Z goes from 0 to 1. Equals. Let's have a look. Do you want me to do this? Or can I just say left as an exercise? Just give you the answer. Okay, because I think at this point you look at that and you think, oh, that's dead easy. How you have grown. And the answer is, okay, I'm going to have to actually look it up. Next one will be a little bit more complicated. Next one is a sphere. Where are we? 50 something. 2. The answer is 2. Okay. Let's do the next one. 53. A little bit more interesting. Find the flux. So we've been given our vector field x, 2y, 3z. Already I can see that my div is going to be just numbers. Yay. And the surface is a sphere of radius 2. Okay, so yeah, question?
The flux question that we got in the past test, would that be considered a simple closed surface?
No, because the surface was not in the slightest bit closed in the test. The surface that you got in the test was that piece of cylinder. It said something like S is a portion of the cylinder, x squared plus y, x squared plus z squared equals 1, bounded at the top by z equals x and bounded at the bottom by z equals 0, and it ends up being that sort of strip of cylinder. But now I'm going to rub all of that out. So if I wanted to do that as a surface integral, for a start I'd need to do 2 surface integrals. Okay? Now, and listen carefully to this is important. When you do a surface integral, you always need to project your surface onto a coordinate plane, right? And that projection needs to be a 1-to-1 projection. There mustn't be any doubling up. And if you take that sphere and you project it onto the xy plane, there's going to be doubling up because the top half of the sphere and the bottom half of the sphere are going to project onto the same disk. And any one point on that disk on the xy plane is really going to represent 2 points on your sphere, the one above and the one below. And that can't happen. If you do that, you end up with a result that's an incorrect result. It's got to be a 1-to-1 projection. So if we were going to do that by a surface integral, we would need to chop our sphere up into 2 halves. I would typically do the top half and the bottom half, but it could be left, right, whatever. But you're going to have to chop it into 2 halves, so that when you project onto the relevant disk on the appropriate coordinate plane, it'll be a 1-to-1 projection, and you'd have to actually do 2 different surface integrals and calculate them separately and then add them up. And you can't just say, okay, I can do 1 and double it, because while our region is symmetric, our vector field is not symmetric. And so the flow through even though the shape, if you divide it in half as 2 kind of equal halves, or 2 sort of mirror image halves, the flow through any one half is different from the flow through the other half because of the nature of our F. So you can't just do 1 and double it up. It's not sufficient that your region is symmetric. It's whatever's happening to your region also has to be symmetric. Okay, so if we were going to do that by a surface integral, it would actually be 2 surface integrals. It would be a fair amount of work. Our n, of course, would have x's and y's and z's in it and stuff. Come to think of it, our n would not be too bad. It would simplify. But still, it would be your common or garden surface integral, and they're always a little bit of work. Divergence theorem makes it a lot easier. So flux, oops, I don't want red, I want black. Flux is equal to, by the divergence theorem, I'm going to call that solid E. This is one of my bugbears. I don't like letters being used in problems that haven't been defined. So if I want to put an E down there, I have to define what E is, which I can either do in words or I can put it onto my drawing. Unfortunately, there are never marks assigned for that, so I can never indulge my bugbear by penalizing people who don't do that. But it's good style throughout any form of symbolic expression of something, that if you're using symbols, those symbols should be defined. Okay, so what do we have here? We have div f is 1 plus 2 plus 3 dv. That's 6. I can pull the 6 out. I now have integral 1 dv. That's just the volume of E. So this is 6 times 4 over 3 pi r cubed. 3 goes into that 2 times. 2 times 4 is 8. 8 times 8 is 64. 64 pi. That's the answer. And that, of course, is the same answer that you would get if you'd done those 2 surface integrals and added them up. But it would have taken you a page. Divergence seems really nice, because div is so easy to work out. Div is often something pretty simple. Triple integrals are really not that hard to do, particularly if the region is easy to define. So divergence theorem is a really, really nice theorem, like Green's theorem is. Stokes' theorem is kind of the problem child that causes some trouble. But Green's and divergence, they just make life so much easier. I'm going to do a page jump. Okay, let me do one more and then you can give it a go. Number 54. Find the flux of f, x, y squared plus e to the xz squared sine xy. And you look at that and you think, oh my goodness, that's a pretty nasty f. But what I can already see is that the nasty bits don't have the variable in them that I'm going to be differentiating with respect to when I do my div. So in the, well, it won't be 0, but you can see on that middle component the nasty bit is the e, but the e doesn't have a y in it. And in the third component, the sine, well, sine's not too bad, but it can give us headaches, but it doesn't have any z's in it. So already, remember, as a mathematician, it's helpful to be able to see just a little bit into the future. Not far, just a little bit. And that little bit into the future, I can see my div is going to be nice. Is that funny? It was meant to be funny. Through the surface of the region bounded. Okay, let's have a look. What does this look like? Okay, that's a parabola. Z equals 0, y equals 0, x equals 0. That's all the coordinate planes. Y plus z equals 2. Looks like that. Okay, find the flux of this through the surface of the region that is bounded by this. Okay, so I'm going to call the solid region E, and the total surface is S, the total surface. If I wanted to do flux via surface integral, I'd have to do 1, 2, 3, 4, 5, 5. 1, 2, 3, 4, 5. I'd have to do 5 surface integrals. I'd have to do 5 surface integrals because that total surface is in fact a union of 5 individually described surfaces. 3 of them would not be too bad because they're on the coordinate planes and that makes them a little bit simpler. This one, the slopey one over here, wouldn't be too bad because the normal to that plane would be easy to work out, but still. And then, of course, the little parabolic bit, that would be the nastiest part. But even if they all end up being not too bad, there's still 5 of them. And I suspect that they wouldn't all be simple. Some would be nasty. Divergence theorem says we can instead do this. Because S is a closed curve, a closed surface, has to be closed. Because divergence theorem talks about a solid and the entirety of its surface, of its boundary surface, not just a piece of it. So because S is closed, we have access to divergence theorem, and we can say the flux is this.
If they left out one of those bounded by, say, z equals 0, then would we say it's not closed or not?
Yeah, so if your surface is not closed, then on the face of it you can't use divergence theorem. However, what you can do is you can say, gosh, I'd really, really like to use divergence theorem. So what I'm going to do is I'm going to artificially close my surface by introducing some bit of plane or something. Then I'll use divergence theorem. However, the answer that I get out is not the answer that I want exactly because there's this artificial bit I've added in. And then you have to take out that artificial bit. And that's what we'll cover tomorrow. So you can still use divergence theorem on a non-closed surface by forcing it to be closed by introducing a bit. But then at the end you have to come and clean up and take away the bit that you introduced. We'll do that tomorrow. So div f is y, catch up with me stylist, thank you, plus 2y plus 0 dv. Okay, I'm going to do that in rectangular coordinates. Cylindrical and spherical are bad ideas. So let's have a look. That's 3y. I'm going to take the 3 out. y. I am going to do y first. Okay, I'm going to treat that little parabolic region over here. I'm going to treat that as my so-called base, and y as my height, and y is going to go first, going from 0 to that plane, whatever it was, 2 minus z. I'll let z go next, and z will go from 0 up to the parabola, and x will go last, so its values of x will go from 0 to 1. A nice little triple integral, just like we saw when we first started triple integrals. Okay, let's do that. That's not too bad. It'll be a half y squared from 0 to 2 minus z. I'm going to take the half out. Actually, I am going to leave it as 2 minus z squared. I'm not actually going to multiply it out. I can, there's no harm in that. But now I'm going to ask myself, what did I differentiate to get that thing? And it's going to be minus 1/3 2 minus z cubed. Multiply out that binomial with absolute pleasure, no harm in doing so, but I can see that leaving it like this actually gives me a slightly simpler expression in the next line. And that's based on having done lots and lots of chain rule and basically just recognizing the forms. Okay, 3's cancels, that's minus a half. That'll be 2 minus 1 minus x squared, so it's 2 minus 1 minus x squared, so it's plus x squared cubed, subtract 2 cubed. Let me just check, am I right? The minus 1/3 I've taken outside the integral sign. 2 minus 1 plus x squared, so it's 1 plus x squared, all cubed, subtract. I think that's right. And then I'm going to have to multiply out. I see in my notes I've just written ... Let's have a look. If I want to cubing a binomial, that's 1 plus 3. So that's that one cubed and none of that. That's that one squared and one of those. That's so that one, and then it's x to the 6 minus 8. So there we go. Okay, cubing a binomial. Okay, and then we ask ourselves, what did we differentiate to get that? And it's x plus, I could have added the 1 and the 8, I suppose. Anyway, that's x cubed, that's 3 over 5, x to the 5, that's 1 over 7, x to the 7 minus 8x, evaluated from 0 to 1. Plug the 1 in, bunch of fractions, add them up, and according to my notes, you end up with 92 over 35. Yeah, because there's a 5 denominator and a 7 denominator, so 35 will be the LCD. Okay, so that particular integral took a few lines, but it wasn't a hard integral, it was all just polynomials, and the shape was fairly easy to describe. I hope you found that shape easy to describe. And yeah, why don't you give it a go? You try the next two. Just see if I'm agreeing with my notes here, number 55 and 56. I'll put the answers up so that you can check yourself. Okay, it's 55, and then the answer to 56.